Okay, let us begin the lecture. In the previous lecture, we introduced Gaussian process models, and in today's lecture, we're going to learn how to fit these models to data that are observed at discrete locations. So in the previous lecture, we looked at some data from Ukraine. We looked at specifically temperature data. You can find the code used to generate this map on the course GitHub page under lecture 2. I'm just going to make this a little bit larger, and I'm going to share it here. So while the temperature is being recorded at these discrete locations across Ukraine, at these monitoring stations, we discussed that it is reasonable to assume that there is an underlying temperature field across the entire country that is reasonably smooth, most likely, and is being realized in these locations and observed with potentially some error related to the temperature measurements. So the goal of today's lecture is to fit a Gaussian process model to this temperature field and then try to be able to predict the temperature at unobserved locations across Ukraine. So we're going to do it. I'm going to show you how to do it, but first we'll talk about a simpler case where maybe look at a one-dimensional input space first, and then continue on into this two-dimensional case, and I'll show you the results of that at the end of the lecture. All right, so this is lecture 3. So the motivation is that we wish to recover the underlying smooth, and we talked about what smoothness means in terms of Gaussian processes in the previous lecture. Temperature field at unobserved locations. Right. So I'm going to show you why a Gaussian process, which we learned about last class, is a good candidate for a Bayesian prior over infinite dimensional function spaces. So instead of placing, for instance, a prior distribution on the discrete parameters of a model, for instance, like weights in a regression, which I'll show you in a second, what we're going to do is place a distribution directly on the function form itself, the functional form itself. So we're going to use this prior model to express our beliefs about this underlying latent temperature fields. So we can incorporate things like our expected smoothness, if there's any periodicity. In this case, there wouldn't be periodicity, or any kind of, for instance, non-stationarity, as well as the scale before any data is observed. So remember, the prior distribution over, for instance, a scalar can be any distribution that describes your uncertainty before the data is observed. Just like you can put a prior distribution over a scalar, so an unknown parameter, in a data generating model, you can also put a prior on an unknown vector of parameters in a data generating process. Or you can also put a prior over a space of functions, of unknown or latent functions that you wish to recover. And the Gaussian process is one very popular and very mathematically tractable model for doing this. So you can use it as a prior model for an underlying latent temperature field, or some kind of risk from particulate matter, from inhaling different types of particulate matter, like I talked about last time. So we're going to look at these two perspectives. We're going to look at kind of a finite dimensional perspective and an infinite dimensional perspective for defining these priors. And we'll see that the finite dimensional perspective is mathematically equivalent to using a Gaussian process model, so a Gaussian process to describe this latent field. And in both cases, we're going to use Bayes' theorem to fit the model to data by conditioning the prior model given the discrete observations so that we can predict the underlying unknown state at various unobserved locations. So one way of thinking about this is that this type of updating refines the space of possible functions to only those that are consistent with our discrete observations. So I'm going to first go back to, explaining what are two ingredients of Bayesian inference, which we know are the prior and the likelihood, the data generating model. But I'm going to describe them in the context of this Gaussian process regression. Okay, so for the two ingredients, first, we're going to need a prior probability model over a suitable function space or a reasonable function space that matches our beliefs about this temperature field before any data is observed. So you can think of this as being like a latent random function. And then we're going to need a likelihood. For the observed data. And this is going to encode the data generating process, which we believe is giving rise to this data. Okay. So let's look at ingredient one, the Gaussian process prior. We're going to spend the most time on this specific ingredient. So there are two perspectives which are nicely laid out in a textbook that I have shared with you called Gaussian Processes for Machine Learning by Rasmussen and Williams. And this book is freely available. There is a link that is provided by the organizers on the course website. So these two views are the weight space views and the function space view of the prior specification. And the reference I will give is the book Gaussian Processes for Machine Learning by Rasmussen and Williams. Okay, so for the weight space view, this is what we typically consider. So consider a linear regression model where we map inputs t into a high-dimensional feature space spanned by basis functions. And you can consider D here, the domain, to be just, for instance, the real line for this simple example. I'm going to put the basis functions into a vector. And then we can write down our prior on this unknown temperature field. So this as a random function, it looks like this. So we're going to take the transpose of this vector phi, and then multiply it by this column vector W. This is a column vector of weights. And so then what we do is we place a Gaussian prior, so a multivariate normal prior, on the weights W. The prior mean, for instance, might be 0, the 0 vector. And we have some variance-covariance matrix, sigma W, which denotes how confident we are about our knowledge that these W's are close to 0. So if we believe that the W's are indeed close to 0, we may think of W as being a diagonal matrix with, for instance, small diagonal entries. Or if we are not sure really what W is, we may want to consider, say, a diagonal matrix with large diagonal entries. So this is just an example. All right, so since X is a linear combination of Gaussian random variables, X is itself Gaussian. And its posterior mean looks like this, or its prior mean looks like this. Transpose. And then the expectation of W, which is just 0. And the covariance looks like this. So X is a 0 mean random function with the following covariance: phi transpose sigma W times phi. So this is what we call the weight space view. So if you're uncomfortable putting a prior directly on a function space, no problem. You can write X as a linear combination of basis functions weighted by this weight function W, which takes multivariate normal priors, a multivariate normal prior. So this weight space view is nice, but it is somewhat limited. So sometimes we wish to put a prior over an infinite dimensional function space. So what we're going to look at is the function space view. I'll just look at it in the finite dimensional case and then mention that it could be extended to the infinite dimensional case. So what we're going to do here is we're going to use a Gaussian process prior directly, which is going to sidestep putting a prior distribution on the vector of weights. And so we're going to assume that X follows a Gaussian process model. So X is a stochastic process. Again, this geostatistical process like we discussed last time. And again, here you can consider D to be the real line, just for simplicity. So we assume that X is a Gaussian process with mean, let's say 0, or it could be M, let's call it just M0 for generality. This would be a function of T, and then with some covariance C0. Okay, so we can directly put a Gaussian process prior on X. So we're going to assume that X is a Gaussian process directly. And then for most applications, we usually take this function M0 to just be 0 for all T. But there are some situations where you might want to specify a prior mean. If you know, for instance, the temperature increases, say from north, going from north to south, for example, then you may want a mean that increases as you go from north to south, just as an example. But we're going to assume that the mean is 0 for the moment. Okay. And here, if we look at the covariance, this is how it's defined to match the weight space view. So these two models, the function space view and the weight space view, under these specifications and setting M0 to be 0, will be mathematically equivalent. So we're putting a prior distribution over a function space that is finite dimensional and spanned by these basis functions phi1 to phi p. But the nice thing about the function space view is that you can now use it to define priors over infinite dimensional function spaces as well. And in that case, the eigenfunctions, and you can think of the eigenfunctions of the covariance function as spanning that infinite dimensional space. So. Or sorry, instead of finding, I should say defining. This distribution directly over X. Okay, and this allows us to use infinite dimensional basis sets, which would be impossible to compute in this weight space. So we, from now on, are going to use the function space view to specify prior models for Gaussian process regression. All right, so let's talk about the second ingredient for our Gaussian process regression for fitting this model to the observed data. And ingredient 2 is the likelihood for the data generating model. So our observed temperature data can be viewed as some realizations of this latent process, of this latent temperature field. But we can also assume that there might also be some measurement error as well. So we're going to incorporate that into our likelihood. First, I'm going to make a quick note about notation. You're already aware of several abuses of notation that have been used so far, but there is one specific one that is common in this area on Gaussian process regression, and I'd like to use it in this lecture because it will enable you to read textbooks and research papers on this area because it's used quite often. So for example, so we will use the notation say C covariance between T and T, where T is a vector, to describe an n by n matrix with ijth element c ti tj. Okay, so C is our covariance function. It takes inputs that are of the same dimension as our domain D, right? But when we write it this way, it is not the same covariance function and now denotes a matrix of these inputs. And this is sometimes hard to understand, when we first look at Gaussian processes, but it does make, as you will see later, our notation a lot more clear when we talk about posterior means, posterior covariances for these Gaussian processes. All right, so here is what we observe. So we observe a discrete set of noisy data. Let's say a finite number of noisy observations. And we're going to denote these as y, and y will be a vector, y1 to yn. Okay, and these observations will be made at these known input locations. And these will be moved into a vector, t1 to tn. And then the t's here, ti, are, of course, in the domain, which again, for simplicity's sake, we can assume that the domain for now is the real line. And so our model for the data generating mechanism looks like this. So our yi's are realizations of this random variable yi, which is a noisy observation of X at input Ti, so the temperature field, if you want to think of it that way, plus some noise that's corrupting our observation. And this noise, we assume some kind of white noise, so it's independent, identically distributed, normal, with mean 0 and variance sigma squared. And we can call that just sigma squared for now. Yeah, there we go. You can have more complicated models on this error. For instance, you can actually use a Gaussian process if you believe that the error actually does vary over the input space. So for instance, if you think that two weather monitoring stations might have more similar errors because they're nearby than ones that are further apart, then perhaps a Gaussian process model here might work. Indeed, you could have a covariance function here that depends on the actual input locations. For simplicity, we're going to assume a white noise process. Okay. All right, and so the covariance, so the variance covariance matrix in this case of the observed values y, and this is going to be the vector of these observations, these random variables here. So the covariance of y is going to be the covariance of the prior covariance on x, so this is c sub 0, plus the error variance sigma squared times the n by n identity matrix, because we're going to assume that these are uncorrelated errors. And again, this notation here, C naught t of t and t, is not referring to the function C naught, it's referring to the matrix that you obtain when you take the entries, the ijth entry to be C naught ti tj. So this is our data generating mechanism. This can be complicated in many different ways, but as long as the yi's are still multivariate normal, we'll be able to use Gaussian process regression to fit this model to data. Some other modifications that we could make would be, for instance, to have a linear transformation of x in the observation process. As long as it's linear, yi will still be multivariate normal, and we'll still be able to update the Gaussian process in closed form. And then also we must have an additive error, but like I mentioned too, we could have a different normal distribution on these errors. For instance, we could use a Gaussian process to define sigma of t. All right. Next, now that we have these two ingredients, we can now proceed to fitting the model to data. So Gaussian process regression is what we call this process of fitting the model, the Gaussian process model to the discretely observed data. So this is done to do posterior predictive inference. Okay, so fitting this model can be interpreted in a way as filtering the noise to recover the most probable latent function that satisfies the structural constraints that we've placed on it through the prior choice, such as smoothness, length scale, and that are imposed by the choice of the covariance. First, let's consider the discrete version. So we're going to make predictions at discrete locations. Let's call those T star, and that will be a vector T1 to Tm. Now, Gaussian processes are more general. In fact, under these assumptions that I mentioned to you earlier, the posterior will be still a Gaussian process. But in practice, when we wish to even plot that Gaussian process, or if we're interested at specific unobserved locations, then we typically have to discretize anyway. So we'll have to discretize the input or provide a discrete set of input locations where we want to predict our Gaussian process. So to make things simple for the introduction, I'm going to talk about this discrete set of prediction locations. But then at the end, I'm going to talk about the result where you can essentially frame GP regression as based on a posterior Gaussian process, a Gaussian process posterior. Okay, so in this part of the lecture, we're just going to use properties of multivariate normal distributions. And so you've seen all this before, and it should be relatively straightforward to understand, so without any kind of function space theory. So to predict the value xt, at these unobserved locations, well, dm there. We write the joint distribution of the observed data and the process, the latent state at the locations where we wish to make the predictions. And again, we have a slight abuse of notation here, where this is describing the realizations of the Gaussian process at these input values T1 to Tm. Okay, so same abuse of notation is happening here. So by properties of multivariate normal distributions, this will be a multivariate normal distribution. In fact, n plus m dimensional multivariate normal. The mean will be the zero vector. And then the covariance will look like this. So the covariance between y and itself, that is the variance, looks like this. And then the covariance, the prior covariance, so between x t star and x t star, is just the matrix C0 T star T star. So this is again the matrix of prior covariances evaluated at Ti, Tj being the ijth element of that matrix. And then the cross covariances look like this. So there are these submatrices, which each element is this function C0 evaluated at one of the inputs and one of the data locations. Okay. All right, so the nice thing about writing this down in this form is that we can use properties of multivariate normal, random vectors to then perform the conditioning. So posterior distribution involves conditioning the prior on the observed realizations. So what we're going to write next is that conditional distribution. Of x at these new predictive locations T star, given the realized observations. So I'm going to use lowercase y here. These are y1 to yn. Right, so here is the final result. So we have our temperature field at these new predictive locations, given the observed data. It's going to be a multivariate normal of dimension m with a posterior mean. And posterior covariance let's say T star I, T star J, for example. As an example, or maybe we could just say S star. Okay. So yeah, maybe yeah. Actually, I apologize. Yeah, let's write it this way. So okay, where the mean looks like this, the posterior mean T star. So we are going to take our data and then we're going to map this into the space spanned by these basis vectors that I mentioned earlier. And okay. So that's the posterior mean, and then the posterior covariance will look like this. So we're going to take the prior covariance. And then we are going to subtract this product. It's quite a long expression, as you can see. So we have a posterior mean, which maps these y's into this new space, and this covariance, which essentially can be interpreted as the posterior uncertainty in the temperature field after the data was collected. And I'll show you how to visualize that in just a moment. Okay. Another comment that I'd like to make is that one of the other interesting properties of multivariate normal distributions is that sequential updating from a normal model that has this conjugacy where your prior is multivariate normal, your data is multivariate normal, can be done sequentially and results in the same inference as you would get by doing the same procedure by conditioning on all the data at once. So this is what's called often called the Kalman filter, but we typically call it Bayesian updating. And it can be conducted in sequence. The updates can be conducted in sequence by taking the posterior from one update to be the prior for the next update. And as I mentioned, the inference that we'll obtain will be equivalent to conditioning on all the data at once. So this, for example, is known as Kalman filtering in the literature. In the signal processing literature, it's called Kalman filtering. It's a very common term, but essentially, if you think of it in a Bayesian way, Kalman filtering is Bayesian updating by sequentially conditioning on each repeated, the following observation and taking the posterior of the previous update to be the prior of your next update, and then updating conditional on the next data point. You can use this when the data is arriving sequentially, or you can just use this when you have a lot of data and you don't want to be doing this matrix inversion here very often. I'll make a few comments about the computational considerations next, and I'm not going to write these down until perhaps later in the lecture if I have time, but the computational cost, so this is my first comment, and the second comment, computational cost of updating a Gaussian process given n data points is proportional to the cube of the number of data points. So it's an extremely expensive operation. This is why in previous lectures I mentioned using Cholesky decomposition rather than, for instance, the inversion function in R. This will speed up the matrix inversion. And yet the matrix inversion in the worst case scenario is still quite expensive. So if you have a lot of data, one thing you could do is assimilate the data sequentially, as I mentioned, using this Kalman filtering approach. There are also other different approaches that people use. For instance, inducing sparseness by using tapered covariance functions. Those are covariance functions that have like a bounded support. And things like a Vecchi approximation, which is a sparse approach that represents the joint distribution of the data as a product of conditional distributions, where you do lose some information. So there is some information loss, but it actually sparsifies the prior. So those are the types of things that people use in practice to make this Gaussian process regression scalable. The next thing I'd like to show you is some visualizations, and the next it will be the code, the R code in the GitHub folder, and that is called GP prior to posterior update. .r. So this script is available on that GitHub page, and I will show you now what that looks like. All right. So here it is. I'm going to run the code. And we have the following, which I'm going to try to maximize here so you can see it a little bit better. Here we go. All right, so on the left-hand side in the first row, you have a visual representation of the prior model in a one-dimensional input domain. So this is not the temperature field, but you can think of this as as some sound waves, for instance, or something else that evolves over. It could be, temperature evolving across time, for instance, at a single monitoring station. So on the y-axis here, we have the actual Gaussian process and its realizations. On the x-axis, we have this is the input domain, so we have t. The lines here represent 3 random samples, so 3 draws of this Gaussian process model that I've defined, and I used a squared exponential covariance with a length scale of 1. Okay, and then these gray bands here represent 2 standard deviations away from the mean, which is 0 in this case, of the pointwise variance. So that sigma that we defined earlier in the notes, that's what that is. So this is twice sigma right here, this distance from 0 to this endpoint. So then after the update, after you've conditioned the prior model by using Bayes' formula, you obtain the following posterior. So these are the data points, these x's right here. So we have only a small number of data points. We have 5 of them. And then there are these colored lines here are realizations from this posterior distribution. So they're samples or draws from this posterior Gaussian process, or this Gaussian process posterior. And then the gray bands again represent actually the same thing as they did in the prior plot. These are pointwise variance. So this is the covariance of t with itself at this location right here. And as you can see, the uncertainty increases away from the data. So in locations that are where the data is relatively sparse, like this endpoint right here, you have quite a bit of uncertainty given the data that you observed, which is expected. And of course, the uncertainty decreases as you get to the data. Of course, the uncertainty here is not 0. These are not totally pinched, these gray bands at x, because we assume that there is some measurement error with variance sigma. And then we have, let's see, yes, and then we have expanding uncertainty between observation locations. And as you can see, the kind of wiggliness of the function is essentially defined by the choice of the length scale, which we did a priori. So if you look at a prior that is defined similarly, but with a larger length scale, you see that these samples now are a lot less wiggly, okay? Their phase variation is much smaller than the previous examples in the second row. And when you look at the posterior, you see that these uncertainty bands are quite a bit tighter. And it is not always true that we want these posterior uncertainties to be as small as possible, given everything else fixed, because this might lead to some bias. So perhaps if the actual data generating function maybe has a kind of different pattern here than what we're expecting given the data, then of course having this kind of lower prior posterior uncertainty will result in some bias, but the goal for us as statisticians is to try to find a prior model that correctly describes our understanding of this unknown latent function. So we must choose ourselves the length scale, for instance. We must choose the prior mean, the prior covariance, and these are all really important choices because they affect our inference, right? You can see the posterior is quite a bit different depending on what length scale you choose. There are several ways to do this choice in a data-dependent way. So things like cross-validation that you might know. So you might want to hold out some data as validation data and try, for instance, systematically different prior length scales, and then pick the one that results in the lowest prediction error out of sample. So for the validation data set. So there are many different ways in which one could efficiently make these choices, but in general, under the Bayesian framework, you would talk to the subject matter experts and really understand how smooth they think this field will be. Essentially, how wiggly will it be? How smooth will it be? So what is the mean square? Is it going to be mean square continuous? Is it going to be, for instance, mean square differentiable a certain number of times? And based on that, you would choose your covariance function as well. So that's one example. And then the second example, I'd like to go back to that Ukraine temperature data. Are there any questions about this particular plot? So this is the goal, is to start with some prior model and end up with a posterior model like this. And this we can use to make inference and prediction at unobserved locations. All right. So then let's have a look at the Ukraine data. I am going to not run this code because it takes a really long time. So I already pre-ran it for you. If I can get it. Okay. Okay, here we go. Okay, and I'm going to try to make it as large as possible now. Here we go. So these X's here, hopefully you can see them on Zoom. These X's represent the locations where we have the monitoring stations. They're right there. And based on these locations, based on the temperature observed at these locations, we're going to condition our prior model. We chose here, just generally speaking, a squared exponential covariance structure and a mean of 0 for this latent temperature field. And this is what the posterior mean looks like. So this posterior predictive mean is actually evaluated at a very fine grid of predicted values. So it's still a discrete grid, right? So we're not obviously we're not going to be able to plot an entire GP, but this gives us an idea what that temperature field looks like. This is the predictive mean. And then the next plot I'm going to show you contains the pointwise variances, so kind of the analog of those gray bands you saw in the previous image. And as you can see, obviously the temperature field is, behaves in a way that is reasonable. As you can see here, the temperature gets warmer as you go further south, and it gets colder as you go further north, which is kind of what we expect. All right, so then the next plot are these pointwise predictive variances. When I mean a pointwise, I mean that these are the posterior variances, the covariance function evaluated, the posterior covariance function evaluated at each of these locations. Okay. And again, what we see here is something analogous to those gray bands. When you see here, when we have several monitoring stations close together, as you can see here, here, and here, we have a small posterior variance. In other words, our Gaussian process is much more restricted near the monitoring stations than away from the monitoring stations. So as you get into these regions here that are not well represented, you see a lot more posterior uncertainty that results from higher variance. And yet you still have information in these regions due to the fact that there is a covariance structure that we specified. We assumed that nearby locations will be more similar in their temperature than locations that are far away from each other. And as you choose a length scale that becomes smaller and smaller, you'll get less and less information in these gaps in the data from the nearby data. And in fact, as you increase the length scale, you'll find that this uncertainty here will decrease in these gap locations. But of course, you have to make a sensible choice of that length scale based on your prior understanding of the data. And also, as I mentioned, you can use some data-driven techniques to be able to choose these covariance hyperparameters. Are there any questions? This code will be shared on the GitHub page as well, so you can recreate this by yourself. Just a quick note, this Gaussian process regression on the temperature field over Ukraine takes several minutes to run. And that's simply because we have a two-dimensional input space, so the covariances that you end up calculating are quite a bit larger. So you have to do a little bit more computation. And there's, of course, the plotting, which takes some time. Okay, great. If we have a little bit more time, we did start a little bit late. I'd like to mention something about the Gaussian processes themselves. So there is a more general infinite dimensional result that I didn't get to yet, and I'm going to talk about now. So the infinite dimensional case, yeah, let's call it dimensional case. Case. And what I mean here is we want to make predictions not at a finite number of locations, but actually just be able to give a general probability, posterior probability model over all possible locations. So over the entire domain. Okay, so the nice thing about Gaussian processes, so just like multivariate normal models, they retain their Gaussianity under linear transformations. So Gaussian process has a similar structure. So if you take a linear operator, so you define a linear operator, let's call it script L, from some Hilbert space to another Hilbert space. For instance, some examples of a linear operator might be integration, differentiation, composition. So these kind of transformations. If we have a Gaussian process that is transformed via this linear operator, we also end up with a Gaussian process. And Gaussian processes can be conditioned on discrete data in a similar way that we saw in the discrete case. So the prior model is the same as before. So it is a Gaussian process over X, this temperature field. All right, and then the data generating model might look something like this. And I'm just being here a little bit more general than I was in the previous example. For instance, we might say that we have that linear transformation of X. And again, we're going to have these independent, identically distributed, zero mean normal errors. And then the posterior distribution is going to look like this. So we're going to have X being a Gaussian process, whereas before we talked about multivariate normal posteriors, right? Because we were trying to predict X at a finite number of locations. All right, and the definition, the way that the posterior mean is written down is very similar to what you saw previously, except we now have this linear transformation, and also this is a mean function here. So let's just, yeah, write it like that. It's a mean function of t star. And t, again, are our observation locations. L star here is going to denote the adjoint of the linear operator. And T are the observations locations. So T. And here T star and S star are just some locations on the domain. So the posterior covariance is just going to be the product covariance minus this additional term here. And again, L star here is the adjoint of this transformation L. So we need a little bit of function space theory here, but the results are analogous to what you see for the multivariate normal case, except I'm introducing a little more complication here by adding linear transformation to the observation process. And I'm also adding a non-zero mean, prior mean. Okay, so this is what the posterior looks like if you want to just think of it as a Gaussian process entirely. Of course, in practice, when we want to plot these things, we need to discretize this Gaussian process. And so we're going to plot realizations of a multivariate normal posterior rather than the Gaussian process itself. So we typically try to discretize at the very end when we have to in practice. And so this is why I wanted to show you how to actually do this without the discretization part. And so this concludes our lecture for today. Thank you very much.